Thank you.
You're welcome, Belgin Hocam. First of all, I would like to thank, first of all, Lee and also you for inviting me to your course. So yeah, my presentation will be mainly about like the basics of acoustics, what is acoustics, why we need it, and what are the basic parameters. And at the end, for the ones who want, we can have a little bit calculation, a little bit math, if they want to participate. Here, I want to open my presentation, but I'm not familiar with Zoom. So maybe Bengi, can you tell me how I can share my presentation?
Can you see the share screen button on the aşağıda görüyor musunuz hocam? Ekranı paylaş kısmını.
Chat, share screen. Aha. Tamam, sunumu seçebiliyorum. Okay,
Evet. We can see hocam.
Now, is it better?
Mm-hmm.
So you can see only the slide, right?
Yes hocam.
Okay, perfect. So yes, welcome again. My name is Zeynep Sevinç Karcı. As Belgin Hoca said that I'm assistant professor in Yaşar University for 2 years, and before that I was a part-time instructor in the different universities, including Yaşar University. Now I'm currently working as a vice dean also. So my background, I'm an interior architect, and I have a eager and wanted to learn what is acoustics and why it's important for interior architects. So I completed my PhD studies in that field. So in my presentation, it will be mainly about the room acoustics and building noise control. So I will start with what is acoustics. Maybe you can interact and tell me, maybe give some words to me when you say acoustics. What kind of images appear in your mind? What comes to your mind? Maybe you can give me some words. Anyone like Retash or Mifida? Do you have any idea about acoustics? Gülnaz, Narmin? Anyone? I don't hear if you are talking. Or Mustafa?
Hi, Hocam.
Yes, Narmin.
I studied architecture but didn't have any acoustic lessons. Yeah.
So poor. Yeah, it's really important, not only for interior architects. Mostly we can say more important for architects, because you need to deal with the building noise control also, because in interior architecture it's more limited with the room acoustics. But you need to have a tendency, or you need to have a little bit care about what is going on in the building, about in the acoustic part. So, okay, when we say acoustics, I will explain it. Then the room acoustics. After that, I will jump to what are acoustic materials. When we say acoustic materials, what do we mean? And at the end, we will discuss the reverberation time. If you have read the articles that I gave you, like the 2 ones, they are mainly focused on the calculation of reverberation time, because it's the common use parameter that we compare our studies, compare the buildings or whatever. So acoustic is, we can explain it, the shape, design, or of a room or a theater or a space that make it good or bad for carrying sound. So for carrying the sound, we need to know better acoustics. So it's a scientific study of sound. When we say acoustic, mainly we are talking about the sound in the atmosphere. So acoustic is a multidisciplinary field. You will see in the following slide what do I mean. But generally, we are dealing with the architecture part, engineering part, physics, electronics, speech communication, mechanical engineering, medicine, and speech communication disciplines. Of course, music, arts, and oceanography are dealing with acoustics. So here is the view of acoustics. You can see what is, in which part we are. It's the yellow lighted part, the room and theater acoustics you can see. When we say acoustics, earth sciences, here life sciences, arts, and engineering, they all deal with it. But in architecture, we are between engineering and arts, which includes electroacoustics, shock vibration noises, musical scale instruments, psychoacoustics, communication, and of course, room and theater acoustics we are dealing with. So while we are dealing with the acoustics, we need to consider that we need to know that it's part of indoor environmental quality. So when we say indoor environmental quality, it includes the lighting quality of a space. Since you're architects and interior architects, you need to be aware the lighting comfort, right? The visual comfort of your users, the oral comfort, thermal comfort, and the air quality. And the acoustic quality, which is really important, but generally it's more like the second, it's behaved like it's the more less important part of the indoor environmental quality, but it's not actually. So the in acoustic wheel, when we talk about the interior acoustic, it deals with the architecture, psychology, science, and design, because your design affects the acoustic comfort of space, which affects the psychology of your users. So you need to know what is happening, how the sound behaves in a room. So when we say acoustic studies, generally it divides into two: architectural acoustics and environmental acoustics. Since we are architects and interior architects, we deal with the architectural acoustics. And like 99.9% of the studies are room acoustic and the building acoustic studies. When we say the room acoustic, it's mostly the volumetric acoustics that we deal. So this is the part more interior architects are dealing with, let's say, because when you're trying to increase the comfort parameters, you need to know the room acoustics. When we say building acoustic, it's more like the maybe the urban noises, or the building, the whole building sounds. If you're working with the whole building sounds or the building and the urban relationship, then you need to work with the building acoustics. And we have at the bottom, you can see 4 different techniques. Okay, we do those studies, but how we do those studies? There are some methods. The first one is, mostly used one is oralization, ray tracing. Those are the more populars. And of course, room acoustic modeling design is also popular those days because we have some softwares, and also predicting absorption performance of the space is also becoming popular, let's say. But generally, we are doing the ray tracing methods in the buildings. I will briefly explain what are they to you. In room acoustic modeling design, there's a program which is Odeon. Maybe some of you heard it. In Odeon, you will see images in the following slides, but I will give explanation now. You model a space, like you have a render, let's say, and you define the noise sources in those spaces, noise sources and the receivers. For example, I'm now in a meeting room right now. I am the only noise source. And if there were some students, someone in the meeting room, they would be the receivers. So the rays, the noise that's coming out of my mind, they hit the surfaces and become reaches to their eardrum. So if you are working with the modeling, the ray tracing method, which is like you work with the rays coming out of the mouth and reaching to the ear. So this is the most common one that we are dealing with. Oralization is more like electroacoustics. In oralization, you have a model and you think that there are more than many sounds, more than maybe 2 or 3 sounds. They become active at the same time, which is mostly focused on the electroacoustics, like the speakers. If there were some speakers in the room and you want to understand how the sounds will behave in that room, this is the method that we do, the oralization. Predicting absorption performance of spaces, this is mostly like a method that we do, but it's like in laboratories, we have special rooms like we call it reverberation room, and we can predict how a material behaves in a room, how they absorb the sound. Also in Izmir, there's one laboratory like that. If you had taken my course, you would see that laboratory. And room acoustic modeling design is more like, as I said, the Odeon, that you will see some images. So when we say architectural acoustics, it's the science of noise control within buildings. It includes room acoustics and building acoustics, as I said. The first application of architectural acoustic was in design of opera houses, then concert halls. First, everything started with analyzing the opera houses. Like we can say that spaces for music, and then spaces for communication also. They thought that, oh, this is important too, and many studies started to happen in those spaces. More widely, noise suppression is critical in the design of multi-unit dwellings and business premises that generate significant noise. So if you want to study in that field, you can study in concert halls, auditorium, churches, conference room, theaters, cinemas, music room, any space that I generally say, any space that a human being can live, can be in it. So you need to think about their oral comforts, like office spaces, like your classroom, like your home, anywhere that you communicate with someone and there's a space. So room acoustic is the science of controlling a room's surface based on sound absorption and reflection. This is important because, as I said, we deal with the sound, and the sound can absorb in some spaces and can be reflected in some spaces. For example, my desk here, probably all of your desks are plywood or any wood that has a covering on it, right? Like maybe it can be shiny or a massive wood, whatever, but if it's shiny, we can say that it's a nice reflective. Or a mirror. We are all familiar that you can see your reflection in on the mirror, but in the sound, it's the same way. If you talk to a mirror, talk to a glass, your sound reflects back into the surface. But if you shout to your clothes, or any soft fabric, soft surface, you can little bit observe that your voice can be absorbed, which means that those materials are absorptive. And when we are trying to enhance the speech intelligibility or the oral comfort in those spaces, we need to, first of all, know the chemistry of the material. We need to know how that material behaves in that room. And second, we need to know how much we need to use each material. For example, think that you're in a Turkish bath, Türk hamamı. When you go there and when you talk, you can see the reflection of your sound like many times, which means that there's a high echo in those spaces. But when you're in your bedroom or when you cover yourself with your blanket and when you start to talk there, you can observe that you're around the absorptive surfaces, your blanket, your pillow, your clothes. Then you can observe that your sound suddenly, not say suddenly, your sound can be absorbed very fast. So those are two different surfaces, two different volumes for us. You can have that experiment. So which is really important for speech intelligibility. So, and also in order to predict the planning of spaces, like when you're designing spaces, like where you're going to locate your rooms, if you are talking about a residential space, where you're going to locate your bedroom, closer to the highway or not. I mean, first of all, you need to know where are the sound sources around your building, around your room. First of all, you need to know them. And second, you need to know how you can pretend the noise coming to you, to the occupants. And lastly, you need to know which material to use where. So as I said, those are the modeling design. Those methods like the modeling, ray tracing, oralization. Those are some methods that we use for different cases, actually. So as I said, in acoustic modeling design, I mean, I already mentioned those. I will skip that. Here you can see on the right-hand side, this is the image from Odeon that we do the modeling, as I said. There are some red points you can see. Those are our receivers. In those modelings, we can predict in the pre-design period, like how the space will be will behave to the sound, like how the space is it going to be a better acoustic, let's say, is it going to have a better acoustic comfort or not, or in some parameters that I don't want to mention all of them here, but for example, reverberation time. What will be the reverberation time of this space? In those modelings, we can predict them. On the left-hand side, you can see the ray tracing method. So here you can see there's a speaker on the stage and audiences. With the ray tracing, so you draw some rays coming out of the mouth and reaching to the receivers. You can see how the reflectors on top of the audiences behave. If they are reflective, you can see which ray is coming to which part of the audiences. For example, when we look at the green part, you can see the first reflector is working for the first 4 rows in that hall. So the first reflector, if you tilt the first reflector, you can see that the reflection would be different parts. So the location, the angle of each surface material is very important for us. This is just an example from a ceiling, but you need to think the rear walls and the side walls. So here our equipments. The images on the left are from the laboratory from BLX, which is in Izmir. Here is a method of predicting sound absorption material of a probably it's a wall panel. This is also another study. For example, one of my students, a graduate student who wants to make a panel with moss. Moss is the artificial, not artificial, they're also green plants, but which we use in the indoors, which is available to use indoors. So he wants to generate a panel, a material with moss, using moss, and he wants to measure it. Like if you use, let's say, 1 panel in its space, what happens if you use 2 or 4 panels in a space? So for those studies, we need to predict the absorption coefficient of those materials. So this is the method that we do. And on the right-hand side, you can see those are the oralizations. So in a space, those are my images also. You can see we locate the speaker on the stage, and we gave sound to the room, and we oralize what would happen in that space. And we have a microphone at the bottom image you will see. You locate the microphone in different settings, and you can see how that person hears each frequency. So when we say noise control, as I said, it's more dealing with the controlling the space that the noise is emerged, let's say. You need to eliminate the source, the noise source at the beginning, first of all. Then, if you can't, you need to switch it with a quieter one. For example, you're living in a building and there's a huge UPS machine right next to your door, generator gibi düşünün. First of all, what you need to do, first of all, we need to cover that machine if we can, of course, with a quieter one. And then if we can't, we need to know how that sound is predicted, is produced, sorry. we have some different methods in acoustics. Is it the air transformed, or is it a solid transformed noises? First, you need to define the problem, then you need to find the solution for that. If it is a shaking machine, let's say, the basic that I can explain. If it's shaking, first of all, we need to change its footage. First of all, we need to put some vibration absorptive materials underneath that machine. Or if it's giving the sound out from air particles, we need to absorb that sound within that space. First of all, you need to know, is it shaking and giving vibrations and producing sound? For example, like that kind of a sound, which is like a structural sound, we say. And if it's like a noise which is coming out of a mount or a guitar or whatever, then we need to have different types of control systems. For noise, we need to know what is the noise source first, and second, we need to know, is it coming from the structural borne sound, or is it a air-borne sound? And for noise control, as I said, it's more dealing with the urban and the buildings. First, we need to know like which sound that we can control under noise control. First, if it's the industrial noise. If you're building like I know that there are architects in the studio. First of all, you need to reach the noise map of your location. First of all, you need to know where's the main noise sources are around your building. There are some maps that you can see, like different colors and different. Here you see on the right hand side the CADNA. Yeah, in CADNA you can see which building is producing more sound. And for example, if you are if you are constructing a building, you need to know the more noisy parts, and you need to locate your volumes according to that. So you need to know, is there road traffic noise, is it the aircraft noise, or is it the train noise, is it the subway noise? You need to know all of them before starting to design. And here you can see on the right hand side, there's an image which looks like a huge thermometer. This is our sound recording machine. We carry it to everywhere, and we can measure the loudness of spaces, loudness of a area. And also with, I'm sure some of you might have it, with your cell phones. Also, you can download some programs, and you can measure the background noise or the loudness level of many spaces. So acoustic materials, as I said, both in room acoustics and noise control, in all of them, you need to know, first of all, the noise source, and then you need to know the acoustic materials. You need to be familiar with them. First of all, you need to know which one is reflective, absorptive, or a diffuser also we have. And then you need to know where to locate which one. So acoustic materials can be absorptive, reflective, or diffuser. You can understand, I mean, I also a little bit mentioned what is absorptive and reflective. Diffuser is much more, diffuses the sound in different angles. And the material quality determines either it's reflective, absorptive, or diffuser. As I said, your tables or most of the walls or glass or mirror, they are all reflective. For a diffuser, it should have different angles on it. You will see some examples. They all have different physical features to control the sound. We need all of them in a space. You cannot just use one of it in a space and reach to speech intelligibility. You need to know 3 of them and need to know where to use them. Here, the reflector, you know, if you had physics in your high school, maybe you studied the mirrors, you need to know the reflection. It comes with the same angle and it goes with the same angle. Those 2 angles are same, you know. In the absorption, some of, let's say you have like 100 sound rays, okay? In a reflection, you reflect almost all of them back into the space. In absorption parts, For example, you say that the half of it is absorbed. In diffusion, it diffuses all of them, but in different parts, in different angles, okay? So reflective materials, they're located mostly on top of the, not noise source, the speaker. Those are different. When we say noise source, it means that we don't want it, because the main difference between noise and sound is noise is an unwanted sound. So here the piano is something that you want to hear. So it's a sound, it's a source for us. So since the sound is generated on the stage and you want to make sure that each person in that auditorium, in that hall, can hear the piano sound at equal intelligibility level, okay? So by reaching that, you need to reflect the sound as much as fast, as much as possible to each seat. So you see different rows of reflectives with different angles, which in one of the images I showed you, they all focus on different locations on the stage. So for example, this, I think that you can see my mouse, right? Those reflectives, which is closer to the stage, 99%, they are reflecting the sound to the first rows in the hall. The one on top, here you see, the sound wave comes from the piano, hits to that reflector, to that reflective, reaches to the, maybe to the balcony, or maybe to the back row of the hall, okay? They all have different aims. And with those reflectors, you can hide the lightings, and there are some HVAC tracks. Maybe you can hide them, which also covers to the back part of the ceiling, let's say. Here are some different angles and different usages. So when I look at those holes here on the ceiling, I can see the reflective materials, but on the side, you can see some diffusers and absorptive surfaces. For example, on the left-hand side, you see blue and darker blue with the white lines. Most of them are absorbers, actually, because it's like the back part of the hall. And underneath them, the black part is also maybe absorptive or diffuser. I'm not sure about that. So in a space, we need to use all of them. On the right-hand side, this is from Sydney Opera House. You can see the reflectives, and also here is the stage. You see the images taken from the stage, and you can see different materials on the walls. Plywood is one of the most used material in those spaces, because plywood, if you have different angles on it, it behaves like a diffuser. If you have holes on it and put a absorptive material behind of it, it becomes an absorber. If you just use it like let's say vanished or verniklendiğinde, if you make the shiny glossy surface, then it becomes a reflective. So with one material, you can have all those three different aims. Let's start with the absorptive materials. For example, a straw board or a pulp board that you have used in your models, right? And the perforated plywood, like here you see, they're all absorptive materials. Here is a perforated plywood. If you do not have a perforation on it, delikler olmasa, if there weren't have some holes on it, then it would behave like a reflective surface. But if you have holes on it, and underneath that, I'm sure there's a glass wool or a rock wool behind it, then it becomes an absorber, actually. And acoustic tile, which is a very good absorptive material. I'm sure many of you have maybe touched it, or you have seen it. If you go to a cinema, please touch the walls. You can see the walls are a little bit softer, which means that they are absorptive, because they want to reach low reverberation times in those spaces. So they have many absorptive surfaces in cinema halls. And other than that, felt is a very good absorptive material, by the way, or fabrics, like even your clothes, even your body in a space, you become an absorptive material in those spaces. Diffusers, as I said, they have different angles, different shapes, which means that the sound ray hits to them and diffuses, goes to different angles. You need to use, first of all, you need to choose one design, and then you can use it spaces where you want to diffuse the sound. In order to decide where to use them, you need to have a model, a 3D model, like a software, like using Odeon or different programs. You need to see how the sound would behave, and then you need to locate, okay, let's put some diffusers at that wall. You will see how the sound will behave. If you think that it's too much, you need to decrease the number of the diffusers. And of course, by deciding it, you need to have some quantitative data in front of you. You need to see, for example, if you put 10 diffuser panels, what happens to the reverberation time? If you put 20, if you put 2, what happens? You need to compare them and you need to select according to that. For example, here are some images that maybe we can discuss. We can see some different materials, like on the ceiling, on the first image. It's a perforated plywood, by the way. It has absorptive materials behind it, because when you're in a space, when you start to talk, it's more like your sound goes, tries to hit to a surface to transfer to heat. That's what happens actually. The energy, the sound energy transfers to heat energy until it reaches the sound travels. So generally the sound travels to, because according to your direction of your mouth, it goes to the ceiling, hits to the ceiling, and then reflects back. If it reflects back or it absorbs, whatever happens, then reaches to the receivers. This is a indirect path of a sound. Also, there's a direct path of a sound, but for the indirect, it's a little bit tricky to control it, actually. So in a classroom, in a hall like that, it's very important. Like if someone is talking, a teacher is talking, your instructor is talking, you need to first see the instructor, because reading the lips is very helping for oral comforts. First, you need to see the instructor and you need to hear the direct sound and the reflected sound, which is bouncing from the ceiling or the rear walls of that space. This is what happens in classrooms, actually. And in offices, like open plan offices, which was my PhD thesis, by the way, there are many different sound sources at the same time. Like everybody's talking with someone, or someone is talking with their phone, or maybe they are having some small meetings. There are different scenarios happening at the same time. First of all, you need to make sure people can communicate each other in a very satisfactory way. And then you need to make sure that they are not disturbing to others. So you can create some cubicles. Like on the right-hand side, you see, like here's a cubicle, like maybe you can have your meeting. There's also, I forgot to say, there's a TV and a monitor that maybe you can have different like oversee meetings, whatever it is. And here you can see the walls of that little space is covered with absorptive materials, also the ceiling. So you need to make sure that people can understand each other in that space, but the sound wouldn't go out from that space. So having some small spaces, subspaces, is very helpful for us, because when the space becomes bigger, it's difficult to control the sound. Here, different images also you can see. Also, here's a kind of a waiting room. Those images from Feltaş, by the way, they are installations. Here you can see there are some absorptive materials on top, which is integrated is with lighting material. You can see there's a hexagon or whatever, 1, 2, 3, 4, 5, 6. Yeah, there's a hexagon light shape, and there are some triangles also. There's a pattern on the ceiling, which is combined with the lighting. So the sound is absorbed there, and also you can have the lightings covered with them. And on the right-hand side, the corridor. Like it can be from a corporate office or it can be from a hotel, I don't know. But the corridors, which generally are covered with marble on the floor or maybe plywood on the walls, whatever is the material, are generally noisy spaces, can become noisy spaces. Also, you don't want to hear people talking. For example, you're in a hotel room and you don't want to hear talking on the corridor, right? So the corridors are also important. You need to absorb the sound. On the ceiling, you can see buffers. We call them buffer planar elements, which absorb the sound. And those materials also, they are felt. As I mentioned, felt is a very absorptive material. And also the lighting is integrated with them, is hung over the ceiling underneath the buffers on the right-hand side. You can see in those spaces we use absorptive materials. Here, on the first image, this is a cloud system, which also looks like a cloud. A kindergarten or where kids play, which is a very noisy sound, very noisy space, you know. You need to absorb the sound. Those clouds, which are also, you can use them within the lighting elements, I'm sure. And here you can see those all absorptive materials. The cloud system, and also again the baffles on the right hand side at the bottom, you can see. And also on the left hand side, you can see probably it's a cafeteria or a restaurant, which is covered with glass. You see, one facade, at least we know, is all glass. As I said, glass is a very reflective material. So in order to balance its reflectancy, you need to have many, as much as absorptive materials in those spaces. So in the ceiling, on the ceiling, they have baffles also. So reverberation time and materials, because in my presentation, I'm sure I have mentioned reverberation time many times. I want to explain what's the reverberation time with 2 slides, and maybe you can understand what I'm talking about when I'm saying it. As you know, the materials can be reflective, absorptive, or diffuser. So in order to use them, you need to know the reverberation time of a space. So, and by knowing the reverberation time, as I said, you need to know which material you need to use, how much the material you will use on which walls, on which parts of the space. For that, you need to know the noise reduction coefficient of the materials, of course. NRC, we call them NRC, okay? I'm not going too much detail, I hope so. So, for having the optimum reverberation time of the space, for example, it differs between a music hall and a classroom. And you need to know the reaction of a material, the NRC value of a material, in order to predict the reverberation time. For example, here there are some NRC values of materials. If the NRC value is closer to 1, which means that 0.9, 0.8, 0.7, which is closer to 1, means that that material is absorptive. But if a material's NRC value is closer to 0, like here, concrete, you can see 0.02, 0.04, which means that they are reflective. 1 is absorptive, 0 is reflective, okay? And here, carpet, you can see it differs from 0.2 to 0.7. If the carpet is fluffy, if it's like 3 or 4 centimeters, daha böyle pamuksu, kalın. If it's a fluffy carpet, which means that it can behave as a observe the material in a space, but it's just a very flat carpet, which is like a very tiny, which means that it behaves as a reflective in a space. So when you're using a material in a space, first of all, you need to make sure the NRC value of that material. And many of the catalogs, maybe after today's lecture, you can look at them in a different way. You can see the NRC values of many materials. So you need to know that value. So for that value, as I mentioned, there are different frequencies in sound. In laboratories, they send different sounds to that material. For example, here is a, let's say, piece of a carpet, and I'm having a measurement on it. First of all, I send 250 hertz to that sound, to that material. Then we send 500 hertz, then 1000, 2000, it becomes more. And then they have a average of it. The average, here are the numbers of averages. Of 250, 500, 1000 and 2000 hertz. So again, we are coming back to reverberation time. Do you remember I mentioned the Turkish bath, Türk hamamı, which means that your sound would reflect back a lot, would have an echo in that space. Türk hamamında ses geri geliyordu. So in that space, we can say that the reverberation time is high. But when you're in your bed and covered yourself with a blanket, and if you shout or clap your hands, the reverberation, since the reverberation time is low, your sound would decay faster. But in a Turkish bath, for example, you clap your hand or you started to sing, your sound would hit a surface but couldn't transfer its energy to heat. It would be really reflective to another surface. And it would reflect from another surface to the ceiling, maybe from the floor, from ceiling. It would go like that. But in your living room or in your bedroom, it will maybe bounce 2 or 3 times. But in a Turkish bath, maybe just one sound ray will bounce like 100 times. We don't know. It depends on the volume of your clapping, whatever. So for reverberation time, we define it with RT60, RT60 here you see. So if you think that you open a source in a space, you open the radio. Okay, actually we use white noise, but I want to make it more easier for you. You open the source, you are listening a sound. It reached to, let's say, 100 decibels. Decibel also, it's our measurement level that we measure the, let's say, the power of a sound. If it reaches to 100 decibels, 100 decibel'e eriştik. You are listening Tarkan, whatever. You are listening something. And then you suddenly turn off the radio. Okay? What happens? Your sound, after it's turned off, the sound would decay from 100 to 0, right? Then it would disappear. We are not going to hear it anymore. So from 100 to 0, when it comes from 100 to 0, in reverberation time, it's said that it is the time a sound level to drop 60 decibels. So from 100 to 40, 100'den 40'a düşene kadar. Or if you open your radio, your Tarkan sound, 60 decibels, and when you turn it off, it is the time that takes that it becomes to 0 decibels. I hope you are fine here. 60 decibel düşene kadar geçen süre. It is the time that a sound level takes to drop 60 decibel after the source is switched off. Here in that graphic, you can see it also. This is important. I'm mentioning it a lot because I will use it a lot. So the reverberation times, as I said, it differs for different spaces. So if you're designing a space for a speech, you need to have a lower reverberation time, because think that you're trying to give a lecture in a Turkish bath. It would be very difficult. There will be a lot of echo and people wouldn't understand you. But in spaces for music, we can have higher reverberation times here, like 2.5 seconds or even 3 seconds, which means that if you clap your hand in a space for music, the sound would reflect to different surfaces for 3 seconds long, okay? But for speech, since the communication should be very satisfactory, and it should be, the intelligibility level should be higher in a conference room, the reverberation time would be really low, for example, 0.5, which is very good for a classroom. But also there are some spaces that we have both functions, like school hall. In your school hall, one day Fazıl Say comes and plays the piano, and then second day someone becomes to give a seminar, maybe me, which is I'm giving speech and Fazıl Say is playing the piano. So it should be suitable for two functions, right? So those spaces should be within here, maybe 1.5 second reverberation time. It differs. So here's a nice chart. You can see for speech lower, for music higher, okay? That's why in your bathroom, when you're singing, you can think that your sound is very good. You can sing in your bathroom because the reverberation time is high, and you could think that your sound is very good. You are like Pavarotti, whatever, but actually you're not. This because of the reverberation time. So for reverberation time, we have a formula, the Sabine and Eyring formula. The Sabine is a very intelligent man who was living in New York or Boston, I think New York. And he have visited many musical, like the theaters, like the concert halls, opera houses, and he was very curious about it, like what is the difference, like why I'm, for example, having different acoustical, let's say, performance, like not performance, like acoustical experience in those different spaces. And then he visited all those halls, and he became with a formula. So he said that in order to calculate the reverberation time, here is T60, but in many of the studies you would see RT, reverberation time 60. He became with a formula. In his formula, which is like we have a constant value, which is 0.16, 61 or 16, minus volume of that space, divided with SA, which is the S lambda, which is the calculated like the surface area and the average absorption coefficient of per band, which means that per each frequency. So for calculating this space, for each spaces, you can use that formula. Even in your room right now, you can calculate the reverberation time by using Sabine formula, which is roughly okay. I mean, which is very difficult to use it in huge halls, but in small spaces like your rooms, which works very nice. And also there's Eyring, which is generated like many years after Sabine. It has different perspective on reverberation time, but the Sabine formula is most commonly used one. So for calculating the reverberation time, in that slide you see like the constant times value and divided with S lambda. For that S lambda, this is how we calculate it. For example, in your space, you have 4 walls, a ceiling and a floor, and you are using different materials. First of all, you need to know the NRC value of those materials. In Google, you can type it if you want, like you can type NRC value of concrete. You can see it in each frequencies. NRC value of a plywood, like curtains, carpets, or NRC value of wall constructions, like the wall layers, you can find them for each frequency I said. You need to know, first of all, the finishing materials NRC values. And then if you put them into that formula, you can calculate your reverberation time. Here is an example. I'm looking at some. Oh, we are almost there. Okay. I want to do that calculation, Belgin Hocam. Maybe if your students want it, maybe you can give a homework. They can calculate their room's reverberation time, looking to my slide.
Yes, why not?
Yeah, why not? So this is a very generic example that I always ask to my courses, like think of a space which is like 3 meter high, 3 meter width and the depth, which is like a cubicle space, and only just one material is used. Think that you're in a space, all the surfaces are gypsum boards. For calculating the reverberation time of the space. First of all, on that equation, you can see on the top 0.16 minus volume. I'm sure you can tell me the volume of the space. En boy yükseklik, which is 27, right? Which is okay to 0.16 minus 27. Okay, I can calculate that. But what happens? The toplam A, the sum of A. On my slide, here you could have seen the surface area minus absorption coefficient of that space. We will do that together, don't worry. So for each surface, you need to know the square meter of that surface and then the absorption coefficient of that material, that finishing material. In my example, which is really simple, at each surface we are using just one material. I generally draw a chart like this. In that cubicle space, how many walls, how many surfaces I have? I have 4 walls, 1 ceiling, and a floor, right? 6 surfaces in that cubicle space. And they're all 9 square meter each surface, which makes the total volume 27 square meter, right? 9 square meter and 27, the volume is a 27, sorry. And for each wall, when I know the square meter of the wall, I know the alpha value of the gypsum board, right? For example, for wall 1, I know for each frequency, I know the alpha value, right? For 125, it is 0.26. So I multiply it with the square meter. For 500 hertz, I know it is 0.05, the alpha value, and I multiply it with 9 again. At the bottom, we will add them together, don't worry. And for 2000 hertz, when I say 2000 hertz and 125, I want to also mention the difference between them. When we say 2000 hertz, which means that, which is very high levels of pitch sound, which is the pitch sound, tiz sesler. Okay, when I say 125, which is like a bass, boom, boom, boom, right? Okay, so which is like a bass and the high frequencies. Here is the low, mid, and high frequencies. For 3 of them, I gave the alpha value. For bass sounds, we will have a reverberation time. For the mid sounds, we will have another reverberation time. And for the high sounds, we will have another. If you do that math, for each wall, you need to know the area and you need to know the alpha value of a material. And then you can have this calculation. For bass sounds, lower frequencies, the first column here, the A value, A değerimiz 14.4. For the mid frequencies, which is 8.1, for higher frequencies, 2.16. So when I put the values into the calculation, I can find the reverberation time for each frequency, which means that in that space, the bass sound, the reverberation of the bass sound is 0.3. But for the higher frequencies, which becomes 2 seconds. For the lower frequencies, it's 0.3 seconds. What is the difference between 0.3 second reverberation time and the 2 second reverberation time? Anyone wants to comment on it? In one space, it's 0.3, the other one is 2. The reverberation time difference. I mean, if you get the average of those 3, you can have an average reverberation time for that space. But in our calculation, we divided them for each 3 different frequencies. Okay, I will explain, which means that for the bass frequencies, it is 0.3, which means that at 0.3 seconds, it takes a bass sound to decay, to disappear, let's say. It takes them 0.3. But for high frequencies, daha tiz sesler için, it takes them 2 seconds to disappear, to transfer to another energy. So in that space, we can say the bass, let's say the bass sounds can absorb better. Oops, just a minute. But for higher frequencies, it takes them 2.
I think Zeynep Hoca break down. We can add this acoustic calculation to your final assignment. I think that'll be nice. Since we don't have artificial lighting and you don't have tools to measure the daylighting, we can't add, but why not add the acoustics calculation at least? And you can ask similar PMV, PPD questions for acoustics as I know of, but we won't include anything else. I will call Zeynep Hoca. If she's done, we will cut. If not, we will continue a few more minutes, just a minute. Work will be uploaded by Bengi soon. Just calculate the
I'm back.
acoustic values of your room or case study for the final submission as well. We will add that for the final, hopefully. We'll go over it next week and then add it. Thank you.
Okay, hocam.
The word is yours, Zeynep Hocam.
Thank
Please
you.
share your screen with us.
It's coming.
And if you have any questions about this homework, please ask Zeynep Hoca now. I think I will handle this, but like, because
Yeah,
it's
you
not
can,
that
hocam.
bad,
Just
but like still, if you have extra questions, please ask Zeynep Hoca. It's a good calculation. We are giving a thermal, adaptive thermal comfort simulation and survey comparison for final submission case study, and they are working in their own rooms. Why not adding the acoustic performance there, so they will have an understanding? Yes.
They just need to Google for the NRC value of each material, And
Yeah.
we need to know the square meter of each material. That's it. If you have
And
any questions,
they have to know the benchmark, so they can see
Yeah.
if the benchmark of the and it was, as I remember, how many. So it's better not to have any reverberation. So it's better to have
it's
zero.
better to have it closer to zero, of
Zero,
course.
yes, so that's their understanding. They can interpret the results accordingly. I will lead them for next week. Thank you.
Yeah, you're welcome. And for some of the materials, like here, I have like 3 different frequencies. Maybe, hocam, they can have just one frequency. Like in many of the materials online, they just give like plywood. Its NRC value is 0.7, whatever. I mean, which means that it's the average. Maybe they can find only one reverberation time, hocam, not like 3 or 4, like I showed here. It would be easier for them, just one.
Yeah, they can try one for next week, and if they are interested, we can.
Yeah, if they're interested,
Yes,
they can divide it into like the bass sounds, the mid and the high frequency sounds. Of course, they can.
okay, thank you. Any
welcome.
questions to Zeynep Hoca? Yeah, let's take a picture for the lay seminar.
Okay.
Everybody, please turn on your cameras. Come, yes, Zeynep yan yana is good. Yes, one student has a missing camera, so they are in class, which they are lucky they are together now. Good to see them. Do you see me by any chance?
Yeah.
Am I there? Okay.
Yeah,
I
you're
don't
here.
see myself. I don't know why.
And Belgin hocam, like I gave 2 readings. One of them is from Porto.
Yeah, I
Yeah,
didn't realize that. Okay.
Yeah.
Oh, the
One of the readings
museums.
is like the museums. There 2
Oh,
of them.
I will recheck the. Thank you
Yes.
for your guidance.
That's why I choose it, by the way.
Yes, we are taking the picture.
Okay.
One more. Thank you for your time and commitment. Good to see you. See you at lunch, maybe, Zeynep Hocam.
Okay, yeah, I will be
And
there.
everyone, see you next week with the final drafts, ready to discuss the details and go over the vision, ne o? Sanal, sanal İngilizce diye artificial trip to tea house. Yeah, we don't do the trip. We don't conduct the trip, so there will be an artificial tour of the house, and
Nice.
we will discuss the final submission, this part, homework, and finally we will review our lecture. Thank you for your time. See you next week, everyone.
Bye-bye.
Thank you, Zeynep Hocam. Maybe see you at lunch. Bye bye.
Yeah, I will be back. Bye-bye.